Okay, folks, I'm going to get started a little bit early today. It's actually turns out this if we successfully manage to go through the three notebooks of this lecture and the conditional portion of the last lecture, which we'll begin with, we will be completing the Fast AI Practical Deep Learning for Coders Part 2 course today. So it's been a long journey, and thanks for joining me throughout and so on. I think the one suggestion / question I have for folks is, at least when I looked around, I found that John O. Whitaker, who is one of the lecturers, guest lecturers, if you will, of this course, he through Hugging Face has like a 3 or 4 lecture Hugging Face diffusers course. I looked into that. I think he has videos for a couple of them and notebooks for all 4. There's a little bit of overlap of the third lecture, but what I would suggest to everybody is, even if we don't go through it as a group here, I think it's a nice follow-on to this course, because it, we've been on this journey to, when we started, we kind of took a high-level view of stable diffusion, kind of played around with it for a couple of notebooks, but didn't really just use that as the reason to dive into the details. And then we've been into the details for all of the following lectures using the mini AI framework. And then we have kind of come all the way back to where we now understand the various portions of stable diffusion, built it ourselves with code that we understand. And now I think it may be time to go back to the high level and use the diffusers library and play with it. So if you folks are interested, that might be something that to follow on with. There are about 3 or 4 lectures of that course. I would highly encourage people to go through it themselves. If there are any questions, please post on the forum. I intend definitely over the next several weeks to pursue that, just so that I can get familiar with utilizing the diffusers library. The other advantage of that, I haven't gone through it, I just kind of identified the notebooks and so on and downloaded them. The other advantage of going through those is most of those notebooks do not use mini AI. They're just basic PyTorch. So if you want to kind of get an idea of how to use the diffusers library and its pieces without mini AI, but use the diffusers library for various purposes, those notebooks serve that purpose as well. So you're not reliant on mini AI and that's a good framework to train and to kind of develop our own models. But if you're just using pre-trained models and the diffusers library from Hugging Face, that does seem to be a good approach. So any comments or thoughts on that? I think you say so, also look
yes.
at. Go ahead, Yuri.
So I wrote something in the chat, but I thought it would be interesting to look at one of latest methods, just to understand how it's different or what's a good baseline to use. I think problem is I haven't looked into it, but I think with the changing method, right? Like right now, there's a new method that's everybody is switching to. So I don't know how useful it will.
If you could post a link to it or something, maybe we can meet again next week and kind of. I think I posted a paper that I don't know when it was published, but at least it was publicized just last week about a 4-step process. I haven't yet read it or kind of tried to understand it. I think distillation of conditional diffusion. So I had posted a link to the kind of the write-up about the paper on the channel. So if people post a few, and if you're familiar, Yuri, with the method that people are apparently switching to, it would be great to kind of post a link, and maybe we'll spend next week, one more week, kind of looking at these different methods and discussing whether there's anything that we can learn from it and try understanding and or applying it.
Yeah, I'll do that.
Great. Any thoughts, Mayank or Emily?
It will be good if we can huddle along and do that Jono's course too. If we can all do that. What are your
Yeah,
thoughts?
I think it's like 4 lectures or so.
Okay.
Yeah. So I'm open to that if people want to kind of discuss that. So next week, we can look at the first 2 notebooks. I'll post the links to it. We can just meet. I don't know that I would be able to prepare and go through it myself, but nevertheless, we can kind of huddle and see what we have each learned from it.
Yeah.
Okay, that sounds great.
Great. Okay, so let's get started with today's discussion. There'll be multiple pieces to it. Again, given the size of the data set, and I'm only now, finally I broke down and I'm looking at creative ways to download all of the data onto Google Drive and not having to break it up into pieces and so on. But I ran into major problems again with the size of the data set. So a couple of these notebooks, I haven't run them myself, or I attempted to, but ran into some errors along the way, primarily having to do with the size of the data that we need to process, not anything having to do with the code.
Yeah, it was
But
4.1 gigs or something like that.
yeah, it's close to 5 gig. I, managed to break it up into chunks, zip it up and load it. And it so happens that I think one of my zip files had some error in it. So after running for about 2 hours or so of a notebook, which means I spent all the credits on Colab, it kind of gave an error. So I have to go debug and then rerun it for another 2 hours. So I was like, well, it's simply not worth the thing to keep rerunning it. Instead, I'll kind of spend the time on something more useful, like running Jono's notebook and so on. So I kind of stopped that, and I'll just use the pre-existing notebooks to go through them. Anyway, the first one, we have to finish up on the conditional part of the diffusion with attention notebook that we built up. In this, if you remember, what we had done was we added attention to our own diffusion unit that we had built up, and kind of, remember that attention is only used at smaller dimensions because otherwise it becomes too compute intensive. So we kind of use it after the first layer, and of course, it's after the first layer for Fashion MNIST. It's actually at either a dimension of 32 by 32 or 16 by 16 in case of larger images that get processed. So but it was unconditional. So the model itself just had the time embeddings, if you will, added to the basic unit diffusion, and on top of time embeddings, there was nothing else per se. Now here, what we are doing is we're adding, or I should say, we added attention on top of time embeddings. First, we just started off without any time embeddings, then we added time embeddings, then we added attention at the 16 by 16 or 30 by 32 size, and then we are now adding the conditioning or conditioning as part of the diffusion unit. So what we do for conditioning is we say use one of the 10 fashion MNIST class, and in this case, but of course, if you use ImageNet, for example, it will be one of the 1,000 classes, or whatever the data set classes happen to be. And so in order to do that, we need to know what each class is. And of course, we know that in fashion MNIST, it's the Y label. So what we do here is we call if the thing that we input to the diffusion unit in each instance is the image itself at time t, the time step corresponding to how much the image has been noised. And then in this case, for the conditional model, we add the label in addition to it. And of course, we provide the noise as well. And the reason for it is then the network will learn to predict the noise, and then we denoise it in the reverse process. So the forward process while training the network will additionally consist of a 3-element tuple instead of a 2-element tuple. Typically, we would have produced 2-element tuples, which is the image and the time step. And corresponding to the time step would be some noise, and that's the noise that we will try and predict. In this case, it will be the image, the time step, and the label corresponding to the conditioning that we want to give. So we use what is called a conditional unit model. And so it is just what I went through. Besides the noisy image, the time step, it will also have the label. And the label is between 0 and 9. Now, how do we convert a number such as 0 and 9, or 0 to 1,000 in case of ImageNet, into a vector? Well, this is a problem we know how to solve, go through an embedding layer, right? So in the forward of the conditional unit model, much like we do the time step embedding, which, if you recall, is the same thing as starting off with the number of filters. So we just do the number of time embeddings is the same as the beginning set of filters we have. And then we put it through a small MLP, 2 linear layers. So it goes from the number of time embeddings to number of embeddings, norm it, and then again batch norm, and then again through second linear layer. Right. Everything else remains the same, the up log, the down log, all of that remains the same as before. So in the forward, we now have not just the X and the T, the inputs, because we are passing in, recall, 3-element tuple, the X, the T, and the conditioning, which is, if you will, a number between 0 and 9 in this case. We use the time step embedding function and pass in the time so that we get a time step embedding back. And similarly, we pass in the class number into embedding layer where we convert the n classes into n embedding, and the n embedding is the same size as the time embedding. And that is just for convenience that now we can just simply add the 2 embeddings. So you can see that the final embeddings that we send to the network is the combination of the time embedding and is the addition actually of the time embedding and the conditional embedding. And then we pass it through the network and we train it. So we train that for about 25 epochs and then do what is referred to as conditional sampling. So in the conditional sampling, unlike in unconditional sampling, we also pass in the condition. So we create a vector with just that number repeated as many times as in the batch, because remember, we are doing the sampling for a batch of images. So we need the C to also be the same number as the number of elements in the batch. And then to our model, the model has learned to denoise something, but it's learned to denoise something of type C because it's a conditional unit model. So when you denoise it, then it will also denoise it into something of type C. Because it has noised something of type C, it will denoise the noise into something of type C. So then the labels are this, and by conditioning it with 0, which is the t-shirt or top, all of our images will then look like a t-shirt or top. So that's what a conditioning diffusion model does. Basically, the conditioning allows us to condition the model and train it this way. Therefore, when we denoise it, it will again produce images similar to what we provide as the conditioner, if you will. So it's as simple as that, as to how conditioning is added to the diffusion unit models. Any questions on this? Okay, the next step we will take along this path is, so far we have been dealing in the pixel space, right? But as we saw at the very beginning, in fact, of the lectures, we realized that, or it was pointed out to us, that the diffusion models have multiple steps. And one of the steps is for the input images to be actually compressed. And in order to work with a smaller amount of data, that's what the compression is used for. And for compression, we use an autoencoder. But as we'll see, an autoencoder is insufficient or doesn't do a great job. So we then move on, for reasons that we'll discuss, to a variational autoencoder. Right? So what that helps us to do is go from the pixel space, where we are dealing with, if you imagine not a fashion MNIST, but ImageNet model, it's a 256 by 256 or a 512 by 512 3-channel images, and that's a significant number of pixels to process. And because we don't want to do that, we want to conserve our compute, we convert the images from pixel space to a latent space, and we operate in the latent space. And therefore, we also need to, when we sample, we are also sampling latent, and then our generator will have to have the ability to generate high quality super resolution images from latent. So that's another problem to solve. So one problem which we make easy on ourselves, less data compute by compression using autoencoder. Therefore, instead of pixel space, we operate in latent space. But then we have to, when we sample, we'll be sampling in latent space. So we also need to go from the latent space back into pixel space to look at the images. So we first start off by just creating an autoencoder, which we have seen, and we have done that in the past as well, right? So we just download what we do in this case is we create first an autoencoder and then a variational autoencoder, and kind of understand what's the difference between the two. The VAE model, it converts, let's say, a 256 by 256 or a 512 by 512 image to, if it's a 256 by 256 and input RGB, so 3-channel, to about a 32 by 32 by 4. And if the original image is bigger, then it converts it to 16 by 16. Okay. So a dramatically smaller model, and we'll do the calculation to see how much smaller it is. So so much of the hard work then happens at the 16 by 16 or the 32 by 32. Right? So do our own VAE for fashion MNIST. So what we start off with, though, is realize that in this case, we are no longer dealing with, when we want to deal with latents, we are no longer dealing with a H by W. We flatten it. We flatten the fashion MNIST images so that we end up building 784 sized vector for each image, a flattened 28 by 28. And then we build an autoencoder, which goes through 2 layers. The first layer going from 784 to 400, and the 400 to 200. And then we go back from 200 to 400, 400 to 784. So that's what this is. It's just a sequential with a linear activation norm. That's what a lin is. Initialization. Remember that in the init weights, the IW that we used to use, right, it only initialized the convolutional neural networks, but now we want it to initialize the linear layer as well. So we add the linear layer here and do the timing normal. Then we initialize it. And first we create an autoencoder. So autoencoder is basically, as we have seen before, it's an encoder and a decoder. So the encoder goes from 784 to 400, 400 to 400, 400 to 200. So 3 linear layers. And then again, a decoder goes from 200 to 400, 400 to 400, and then 400 to 784. 84, yes. So we build the autoencoder, initialize it, do the forward optimization function, do a learner, find out what the best learning rate is, and we train the autoencoder. And then we grab a batch of text from it, and then we convert it, put it on to the CPU to visualize it. And what we find is this is our original images. These are our original images. And then if you look at the autoencoder, you can see that it's not that great, right? It's much better than it used to be before. But for example, the writing here, which clearly says Lee, kind of disappears. This shirt is fuzzy. A couple of the others aren't too bad, but the pattern on this is mostly gone, and so on. So what we try to do also is remember that in the sampling, we used to add some noise and then try to get the image back. So we generate some noise, and since we have a decoder, can we start from a noise and then decode the noise and see what it creates, right? So you take a noise the same size as our batch, and then see whether the decoder from the noise, whether the decoder can give us the output. And the sigmoid is to get it within 0 and 1. And what we find is it doesn't generate anything great at all. And as he says that what we don't seem to have with the decoder, I mean, the encoder obviously compresses the data. There's no problem there. But with the decoder, there doesn't seem to be an ability of the decoder to generate the fashion amnesty images. So it doesn't generate anything great. So the reason for it, as he explains, is that there's no inherent reason why when we take a random 200 sized vector and supply it to the starting point of the decoder. Remember, we have now compressed the data going from 784 to 400, 400 to 400, then 400 to 200. But when we go in the reverse direction, start off with a random values of 200 and then try to go up, so to speak, of the unit from 200 to actually the autoencoder here. We aren't going to the unit, just the autoencoder. So 200 to 400, 400, 400, 400 to 784. We don't get much of anything they look like. So the point here he makes is that when we generate a random vector of length 200 for the batch size 16 vectors of 200 and decode, there's no particular reason to think that the images it will generate will somehow be fashion amnesty images. Right? These are just random values that we are inputting as our starting point is just random noise. So why do we think starting from random noise with nothing, no reason at all for the decoder to give us fashion amnesty images? So what we try and do, and this is the beginning of building what is referred to as a variational autoencoder. And so this is a description of what happens there, but I'll just talk to it in the code. So here, what we do is we split the decoder, we split the encoder. The last layer of the encoder, you see, no longer exists. It's only a 2-layer sequential for the encoder. The last layer is actually split into 2 parts. The first part generates something called the new. The second part generates something called the LV, or what we learn is the log variance. So the first, and remember that the sizes, or at least notice that the sizes of both are the sizes NL that we started off with. That is what the original 3-layer linear network did. It went from NH to NL. So what we are now doing is splitting that third layer into 2 linear layers, one going from hidden layer to NL that NL we call mu. So there'll be a mu value of the size of NL, and there'll be a log variance value of the size of NL. The decoder has no change whatsoever to it. So that's what is described here, right? So we have two 200 long batch latents that we have created by splitting the last layer. And so the random numbers will now have a mu of 0, a mean of mu, because we will generate, if you look at the code here, we'll be generating or picking from random numbers with a mean of 0 and then adding mu to it. Therefore, its mean will be mu. And then standard deviation is just the square root of the variance, and the log variance is what we use as the second layer. And then we pass those values along with the input image through the decoder, right? So what does this do? What it practically does is it adds a little bit of noise, but it also tries to ensure that the mean and the variance are kind of 0 and 1 for the distribution. And as we'll see by the use of loss, we'll try and make that match the incoming distribution. So those are the two things we are trying to accomplish by playing with this encoding network, splitting it, making it create the mu and log variance. So if we optimize this kind of modified, therefore called variational autoencoder with a binary cross entropy loss, then it would generate kind of the SD generating layer, which is the second final layer. The first final layer will be the mu generating layer, and it will kind of turn those into zeros. So the behavior of this network would be very similar to the previous autoencoder, right? But what we want to actually do is to introduce some variance. Why do we want to do that, introduce some variance? That's because what we are aiming for is not to precisely regenerate the image, only if the input image is exactly, or so that the output image is exactly the same as the input image. But if we were to be in the vicinity of input image, that is in the space of images, if we find a point and our noise is close to somewhere in the vicinity of the input image, we want to be able to translate that to an input image. So not just a precise autoencoder where we only supply input and the autoencoder provides an output which is identical to the input, but it's our autoencoder capability is enhanced by enabling it to predict the input or give the output as close to the input, even when the input is somewhat close to the original input and has some noise added to it. So this is a more robust model, and that's the idea of a VAE, right? So there are, by the way, there is a whole literature on variational autoencoder. I provided some link in the notebook itself. In addition, if you're interested, I would also point you to, let's see here. We went through this, I think mine was part of the course. I don't know, Yuri, whether you were there, but there is a whole lecture and a series of notebooks that we went through. It was an NYU-based class. Unfortunately, the explanations offered are from an energy perspective, because in the NYU data science class, which is based off of lectures by Jan LeCun, he kind of takes an energy-based approach. And the simplest way that to understand these lectures and translate energy to probability is if you think of, energy as the inverse of probability, then, I think you'll be very quickly up to speed on any energy-based explanation. But I'll post the links to it. There's also excellent unsupervised learning course that we went through. The lectures are still there, I believe, in Slack. And I think I posted a link to it. It goes through a lot of math on the derivation of why we are doing exactly what we're doing. Jeremy explains it in a much more intuitive way without going through all the math. But if you really want to understand the math behind variational autoencoder, you can listen to this lecture and the corresponding notebook and or the slides, and you'll get a much better understanding of the math behind it if you are so inclined. So the bottom line is that here, what we are trying to do is create a more robust model for our autoencoder. So the question is, how do we get the neural network to generate a log variance, which is the log of the variance, right? That doesn't just simply go to 0 as our network would do otherwise. So in order to do that, what we do is we have a second loss term. Before we go there, the one thing I should explain is in the forward path, we have created in the encoder self.mu and self.lv, right, which is the last layer of the encoder, which has been split up into 2 layers, and then we get the mu and lv. So how do we use the mu and the log variance? The way we do that is to create a v whose value is centered on the mu, therefore the mean, and then multiply it by e to the power of, that's why there is this exponent, e to the power of 0.5 log variance. And the 0.5 log variance, if you think of variance, is standard deviation squared, right? So when you take the log, then it becomes half. And when you do that, then you just, the 0.5 eliminates the, so you just get it as the standard deviation. And then you multiply that by the torch and by the log variance. So what we're doing is we're just kind of creating a z using the mu and the log variance. And then we decode the z and also send out the mu and the log variance. So instead of decoding just the x, which comes out from the encoder, we convert it to a mean and a log variance, use the mean and the log variance to generate kind of the latent, and push that latent through the decoder, as we see here. Now, how do we train this network? So the purpose of that training is to generate a log variance that just doesn't simply go to 0. And to do that, we add a term called the KL divergence loss. And I think we've seen this before, but KL divergence loss is where we try to make the KL divergence is typically used in order to measure the distance or the similarity, I should say, rather than distance between 2 distributions and narrow that gap, right? So the VAE loss takes the binary loss between the actual decoded bit, which is the input 0, and the target, and then we add to it the KLD loss or the KL divergence loss. So now the VAE loss has 2 pieces to it. It has the what is called the reconstruction loss, which is we want the image to be the replica of the input. That's comparing the input to the target or the output, and we use MSE to compare them. And then we add what is also known as a penalty term, which is based on the KLD or KL divergence loss, right? So the BCE loss uses only the predicted image and the actual input image. So that uses the MSE loss between the input image and the output image. That's one part. On the other hand, the KLD loss doesn't use the image at all, doesn't use the input image. It only uses the mean and the log variance, right? So we don't use the predicted input image either in the KLD loss. So KLD loss returns a number which says for each item in the batch, is mu close to 0 and is the log variance close to 1, right? Then now the way we do this is minimizing this equation is equivalent to creating the goal of making the mu to be 0 and the log variance to be 1. And in fact, that's essentially what he shows here, that when you take some random values and then plot the figure of what are we plotting? We are plotting the output, which is 0.5 times 1 plus x minus x exponential. That figure looks like that. And this essentially says we are optimizing it so that when we optimize that, then we minimize mu or make mu 0, right? The lowest you can get, right? And the other piece is the log variance minus the e to the log variance, which is the part that's here, right? And if you plot that and add and subtract, so we do what he's trying to explain is the KLD loss. So we do the minus KLD loss is defined this way with this equation. And what he has plotted is that equation here. And when we do that, we find that the minimum is appropriately obtained. So at the minima, the value we use in the forward method is e to the 0 or 1. So at the minima, the log variance exponent is going to be 1 and the mean mu is going to be 0, which is what we are after. So through this process, and in fact, all the math that I pointed to in the other course, it just leads you through the details of getting to this point where we are saying, okay, what we are doing by using KLD loss and deriving the mathematics behind KLD loss and why we use the equation that's shown here is to ensure that the mu is 0 and the log variance is 1 at the minima that we choose. And if we then use those values, provide to the decoder and train with both a reconstruction loss and a KLD loss, which ensures that we'll have a mu of 0 and a log variance of 1, then we get a much better result from our decoder, from our autoencoder. And this kind of an autoencoder is called a variational autoencoder because we introduce some amount of variation, and this network is much more tolerant to having some noise around the input and still being able to generate the exact input. So KL divergence, as I said before, explains how the two distribution, or not explain, but it tries to minimize, the KL divergence is minimized when two distributions are close or identical to each other. The closer they are, the more, the lower the value of KL divergence, right? And a normal distribution can be fully characterized by its mean and variance. So that's why we use the KLD, and it calculates the similarity of KL divergence between the actual mu and log variance and the distribution that we generate, which will have a mu of 0 and a variance of 1. So, and I provided the link here as well that you can go through all the math if you're so interested. So instead of the exact point of the input being decoded back to the input, the space around that input point will now be decoded into the input, right? And the overall space should be roughly 0 mean and 1 variance. So that's what we ensure. So we have two pieces now to the loss. One is the reconstruction loss, as it's called, and the other is the KLD loss. We combine them and we have the VAE loss. So that's what is shown here, right? So there is a penalty term as it refers to, and you can kind of understand in an energy context through the lecture that I have pointed to as well. And I'll provide the links once we are done in Slack. So we add these two. So the reconstruction, now, one other thing to highlight here is the KLD loss, you see, does not use the input image or the predicted image. So it's almost like it doesn't care about the actual values of the image. It only cares about the mu and the log variance of the input, right? So that's what it is focused on. Whereas the binary cross entropy loss is only focused on the input image and the predicted output image. So one piece of a loss is focused on the reconstruction of the image. The other is focused on the distribution of the output. Does that match the distribution of inputs that we have had? So one focuses on the distribution, the other focuses on the exact nature of the particular image, and the combination of those gives us the VAE loss. Right? So now there's also this interesting question, and he kind of is beginning to play with LLMs also in the course, because he says, okay, I popped this question to Bing and look at the answer it generates, and the answer is pretty good. You can think about what would happen if the variance of the latents that our variational autoencoder generates, if it were very low. If it's very low, then, and what happens if the variance is very high? What happens in the two extremes of the variance, right? And the answer that it gives is pretty accurate. So if the variance of the latents were very low, that means, the log variance is also very low, then you can think of the encoder distribution being very peaked, right? That means it would be a very tight distribution because the variance is very low. And if it's peaked and concentrated around the mu or the mean, then this makes the latent space less diverse, right? Because it's narrow. There's not as much of a diversity in the latent space. And therefore, the decoder is then limited in its ability to generate data, right? To reconstruct the data. Therefore, it also makes it harder to generate new data that are different from the training data, because there isn't that much variation that the decoder can work with. On the other hand, if the latent variation, the variance of the latents were very high, then you can think of it as it's almost like a flattened distribution. It has a peak, but it's very widespread. Now, if that happens, then the distribution is very diffuse, right? This would make the latent space more noisy and extremely random. Or I shouldn't say extremely, because the random is random, but it's more noisy. And this reduces the correlation between the latent codes and the data, right? And when that happens, it kind of produces a generic averaged image. It doesn't, again, do a good job. So if latents are too, or the variance of the latents is very low, then you do not get variety. If the variance of the latents is very high, then you just kind of get a averaged mush, but you don't get crisp images either, right? So it would make it easier to generate new data, but the new data is unrealistic or nonsensical. It doesn't quite resemble the input image or provide crisp, clear images. So we kind of don't want either of these extremes. We want the latents to have variety, but at the same time, be faithful to the input images that we provide, right? And the first part, where we train the latents to be, or the variance is very low, that's almost the same as having no KLD loss at all. And that essentially says we just get the input image precisely. So the latent behaves this way. Right? So when we train the VAE, we'd like to see how well the VAE is reconstructing the original image. That's the reconstruction loss. And how well is it creating a zero mean variance 1 values. That's the KLD loss, right? So he creates two metrics, the functional metric derived from the mean class of TWIML metrics, and create a custom metric wherein we can pass in some function. We call two metrics. One is for KLD and the other on DCE. We add that, we train the network, fit it, and as you can see here, The third element is the VAE loss, which is a combination of the KLD and the BCE loss. Right? And because we have kind of added the noise and so on a little bit, this is a harder problem for the network to solve. It's not going to be easy. We have not made the problem easier. It now actually needs to get the input image back, even if the original image that we provide is not exactly the input image, but is input image with some noise added to it. So we train that, we do the VAE sampling, and then, as expected, it's even worse than our AE, if you will, because we kind of, added noise and made the problem tougher. But the reason we are doing this is to say, hey, can we get a better value if we started off from noise, right? So the hope is when we call on random noise, we get something better. And what you see is that is in fact true. While we are not getting very crisp images, it is true that these images are a lot better than just the auto-encoded images that we saw when we try to extract things from noise. This is what we get if it's just an AE versus a VAE. And if we have a VAE where we map the distribution, introduce a KLD loss, along with the reconstruction, then we get a little better here. Right? But the reality is, this is, not just, we have again not trained the network exhaustively. We have just done a very quick, 20 epoch training. If on the other hand, the idea is that if a pre-trained VAE, which is trained on an enormous data set, such as the ImageNet and so on, if we were to use that, then the compression part of the VAE can be used to create latents. And we don't need to recreate the latents each time. We can just use or store all the latents that we create once, and then just operate the decoder on the latent space. Right? So the VAEs are very good for compressing, and they're not that great for generating the images. And for generating the images, we'll see what else we do in order to get a good generation. But what a VAE, or at least the encoder portion, does is it allows us to provide very good compression of the data to generate the latents. Any questions on this notebook? Okay, and then let's go to the last two notebooks are the ones that where I haven't, as I said, I did attempt to, but ran out of space and stuff and gave me an error at some point. But anyway, let's just go through this. What he does here is he uses, in fact, a fraction of LSUN dataset, which is a data set of bedrooms. He uses a fraction of it, which he stores in an OS S3 location, downloads that, and then what he's doing here is using a pre-trained autoencoder. So you grab an autoencoder that is pre-trained from the diffusers, put it on the GPU, and he just says, okay, as long as you say required grad equals or required grad false, then you don't have to save it dot no grad. So we get mini batch, get 16 items of 4 by 32 by 32. And that's where he compares. Now, if you consider the original bedroom images, which are 256 by 256 by 3, 16 of them, and then you compare them to 4 by 32 by 32. I mean, you can obviously get rid of the 16, but the ratio is 48. So you've achieved the 48x compression of the image by using the encoder of the pre-trained VAE. And this is an autoencoder KL from this stable diffusion library, if you will, Plugin phase. And then what he does is he's just trying to look at the latents at this resolution. So, and here, because there are 4 channels, you just try to grab the 3 first ones and show them. And then you need to do the sigmoid because the values, these values are no longer between 0 and 1. But what you see is, if you compare these images to these original images, let's focus on one of them. Let's say we choose, well, the first one with 2 characters. You can see they're still vaguely there. If you look at, let's say, this image, bottom left, you can see this vague notion of some window with something going on there. There's a bed. You can kind of see the structure even at this reduced resolution, right? And what is done though in the VAEs is, one other thing to mention that is sometimes the VAE is also called an F8 in terms of the nomenclature, and that is because the dimensions are reduced by 8 in each case. This is 2 to the 8, this is 2 to the 5, so each of them is 2 to the 3. So each dimension is reduced by a factor of 8, so they sometimes refer to it as an F8. So this VAE that we are using is actually not even trained with just the 2 losses that we saw. We saw the binary cross entropy combined with the KLD when we did our own training. But in full-scale VAEs that are pre-trained and that are publicly available, there is 2 other losses that they add, and we'll discuss those 2 losses here. There's a perceptual loss objective, and we have kind of looked at perceptual loss and understood what it does or what it is and how it works in our time transfer notebook, right? Basically, perceptual loss, what it does is you train a classifier on the same data set, and you kind of pick some layers, some specific layers, and then ensure that the loss of your network that you're training, some layers that you choose of the same dimension and of the same dimension in the classifier, you kind of make sure that they resemble each other. So that's, or the loss between them is minimized. So that's the perceptual loss objective. In addition to that, there's also something that's done, the 4th loss. So there are 4 loss objectives: a BCE loss, KLD loss, perceptual loss, and then GAN loss, or a patchwise GAN loss, or a patchwise adversarial loss. So what is a patchwise adversarial loss? So he explains that here, if you're familiar with GANs, they're made up of 2 portions. There is a generator, and then there's a discriminator. So what we try to do is you take little sections of the images, those are referred to as patches, and you pre-train the classifier with either a real patch from a bedroom scene. So this is an actual patch from a real image, or a patch from some noise, right? Or a fake patch. And you kind of provide those to the discriminator and tell the discriminator to provide a probabilistic output, which indicates whether the patch is real or not, right? If the output is very low, if the probability is the output of the network that you're training, if the probability output is low, then the network is spitting out patches which are easily recognized as not real. And so when we train with this loss, it will give you, obviously, when you use this loss in output, what it does is it provides derivatives which tell you, how do I move this fake patch in order for the discriminator to be fooled and get the fake patch to be closer to the real patch, right? Because then the probabilistic output of the network, the discriminator output, will become higher, right? So how do you change the pixel so that you can trick the discriminator of the GAN better? These then can update the VAE, which is the generator, right? So you do that piece first. So you kind of keep the discriminator and provide it and get the generator. You're training the discriminator to be better at discriminating between fake patches and real patches. Once the discriminator is really good at that, then, or the generator gets so good because you're using the derivatives that are coming back from such a loss to improve the patch, the fake patches to be close to the real patches. So the generator is doing such a good job that the discriminator is getting fooled every time, right? It always outputs a high value saying, whatever patch you provide looks to me to be a real patch. And at that point, you fine tune the discriminator by putting in your better generated images. And once the discriminator gets better, you can use that new discriminator to train the generator to get better. So it's like a ping pong exercise where you first improve the generator. Once it gets good enough to cheat the discriminator all the time, then you stop that and you improve the discriminator, and then you go back and forth. So that kind of training, and there is again a link that will provide in Slack of where Jeremy goes to GAN in one of his previous courses and how you define this adversarial loss and what's the process to go through a GAN. I'll mention that as well. And this whole process generates a loss, which is called the adversarial loss, right? The issue when you do this at low resolution is, or actually, how does the adversarial loss help? Well, at lower resolution, if the neural network is hedging its bets, by hedging its bets, it's just generating average values. It doesn't generate crisp, clear, it's not making distinctive choices between the pixels. It kind of just averages the pixels and gives you an average. Then what this adversarial loss does is it forces it to make better choices. That is, it forces the network to say, no, you can't just give me an average of all the pixels. Make a choice and force the values to be closer to the real patches, if you will, right? So it's not just that it can provide a blurry input so that its MSE loss is good. So you now have 4 things which you have to combine in order to train a full-fledged VAE: a BCE loss, a KLD loss, perceptual loss, and on top of it, adversarial loss. So BCE loss, KLD loss, perceptual loss, and adversarial loss. And this is the lecture in which he talks about, Jeremy talks about the GAN loss or the adversarial loss. So this VAE that we are using now has been trained with all these losses. So if we now use the decoder of the VAE to produce the image, you can not tell the difference between what was the original image here and the VAE produced images which are here. You have to really focus and kind of narrow down the details. One of the details is the fact that it does a poor job of lettering and reproducing the lettering. So if there is any lettering on the image and you focus on that, then you'll find that, it doesn't give a great output that resembles the input if you focus on just the lettering. So the other point he makes is that people often call the VAE encoder when you're training a model, but this makes no sense because the encoded version of the images, that is, once you have a VAE and you pass the image through it, you're always going to get the same latents. So once the latents are generated, there is no reason to again use the VAE encoder. You can just store the latents away and just use the latents, right? The only time when we need what we need the VAE for is to decode the latents, right? So that's what he points out, making no sense to, it makes more sense to just do a single run through and then encode all the latents just once, right? And you can kind of store it. And here he shows a creative way called memory mapped IO, where instead of storing all of this data, which is significant as Mike just mentioned, you kind of store it in disk. Now, storage wasn't a problem for me, but it's the fact that, there were some errors as I tried to transfer all of the data, which is about 5 gig, originally into my Google Drive. So I have to find a better way to transfer data into Google Drive. Larger amount, and I found a tool. I'll post later if I'm having any success. So you generate the latents, you create the memory map in NumPy, and after that, you just have to read the latents. And then you decode the latents that we read. And as he says, zipping the latents makes very less sense because the latents have already been kind of compressed from the original image. And then you get this image. And there's not much difference, as I said. And then now that we have the latents, we can just use the same thing that we used to do before. We can do the noisify on the latents, right? And we create and then test the images now using the noisify. We can decode the noisify images, decoding random noise. But remember, when we decode it, what we will get would be latents, right? Because we are noisifying latents. So obviously, when we decode it, we'll also get, actually, after you go through the decoder, you'll get the original image. But if you're just going through the denoisifying process or the reverse sampling process, then eventually we'll have to add a decoder of the latents to get the original image. So then you train it, you train the original network that we have built, and it takes a few hours of training on a single GPU because it's a single GPU. And then we use the diffuse, he says instead of our own, we can use the diffuser unit as well. Trained it for 25. He saves it and then he samples, right? Now, after sampling, we have to make sure that we decode it, right? Because we are operating in the latent space, not in the pixel space, right? Because the thing we are using it, or the network we're using to train, is actually training on the latents. So if you do that, and then we create outputs of 256 by 256 pixel, and it's pretty interesting that you can see almost realistic images of bedroom scenes after the network is done, right? So he says that we can, the ability to create 256 by 256 images where even at least some of them look like real bedroom scenes is pretty incredible after just a small number of hours of training. But this wasn't possible before, and as Yuri points out, maybe it's gotten even better now to where you don't even have to go through this level of training or this much compute and so on. And then, one of the lectures trained the whole thing for 25 epochs for 15 hours. Unfortunately, I can't do that because Colab cuts me off after about 8 or 9 hours at most on an A100. And that training for about 15 hours on an A100 will probably, each hour is about 13 credits, and I only get 100 credits per month for what I pay. So you need to be aware of the compute costs of doing this kind of stuff. But you can see it produces, good images. Look at this. That's impressive. And so the point he also makes is, when we had this super resolution notebook and we used pre-trained model and used perceptual laws, we got much better results, right? So similarly, what you could do is use a pre-trained model, right? Which would then enable us to not train the model ourselves, but use a pre-trained model. But in order to do a pre-trained model, we now need a model which is pre-trained on the latents, not on actual images, because you have to train it on the latents, not on 256 by 256 original images. So, and then if we put our downsampling backbone of the unit and load its weights with this pre-trained on the latents network, then that unit, which is trained on the latents, can really get to be very good. So based on that, what Jeremy did, and that's what his next notebook is, he again downloads the entire ImageNet data and trains. If you can grab ImageNet from Kaggle, it has the whole ILSV, or I forget what it's called. Yes, ILSVRC directory on Kaggle, download the whole of it. And then, you can kind of, if you're interested in doing that, at about the 1 hour, 14-minute mark of the video. And then there's a whole notebook where he tries to do that, where he's just training a network on ImageNet's latents. So he compresses it and then kind of trains the network on it. But I haven't bothered to run this notebook because it's too large. Otherwise, he builds the same unit. Sorry. Latency idea being that if we have this, then we can load that onto our VAE, the encoder part, and get a really even better network. And then he does another thing called simple diffusion, where he just uses all the things he has built in order to kind of create a very simple network to be able to decode the latents and provide good images. That's pretty much it for this course. Any comments, questions, thoughts? One thing I would encourage people to do is definitely go through some of the details on autoencoding and why we do this splitting of the encoder into the mu and the log variants, and why we have the equation that we do. Those things are important to get a grasp of the math behind the intuition of what we're trying to do by introducing tail divergence loss. And if you're so inclined, also you can look into how the adversarial loss helps. So there are like 4 losses that get combined in order to train a VAE on these large images: perceptual loss, KLD loss, binary cross entity loss, and the adversarial or GAN loss. Any thoughts, comments? Okay, and I'll post, let's see, I can quickly show you guys what created kind of the, here is here's the materials for the Hugging Face diffusion models course. And originally, John just provided the notebooks. There are a couple of notebooks for each of the, let's look at so you can see here, a couple of diffusion notebooks, introduction to diffusers, diffusion models from scratch. And then there is a unit 2 where there is fine tuning and guidance and class conditioning. Then there's a unit 3. Unit 3 is kind of identical to our lecture 9A in this course, which essentially, in fact, unfortunately doesn't have that particular notebook, but basically he has the O1 stable diffusion introduction, and he has a deep dive into stable diffusion, which is what is the equivalent to this. This is preliminary, whereas the deep dive is actually a deeper dive. And he has combined some of the elements from his first two lectures. This particular unit doesn't have a corresponding video, but the video of lecture 9A from our current course pretty much covers this unit. And then we have unit 4, where he actually does the implementation of the DDIM inversion. And he also takes us to an example notebook of diffusion for audio, but this particular unit doesn't have any video associated with it. So we'll just go through the notebooks if you are interested. I intend to go through them over the next week, but I don't know that I'll be prepared with any kind of discussion stuff. So let's just all kind of join in and see what the notebook says and how much success we have had or questions when we play with these. These, I think, ought to be, they're also compute intensive, but I think they are a lot less data intensive. So we should be able to kind of really run because we are using most of the library from the diffusers. And then using Dream Booth with some of this stuff. You can kind of, the fun part of this is now that we understand how each of the details work, it's good to actually play with the end results. I mean, some of these should look very familiar by now. The unit, he obviously goes through a much simpler example. You know, it doesn't bother about time embedding or attention or any of those kinds of things, right? But actually, I take that back. He is using attention, but he's not using. I don't believe he's using any time. So anyway, we'll spend more time on it next week. Okay, comments, thoughts. If not, done with this. As I mentioned, it's been a long journey, but thanks for joining, and should be done. And with this part of the course, we'll just spend maybe 2-3 weeks max for the Hugging Face diffusers and its various uses, and we should be done with it in a month from now at most. And Yuri, if you can post any interesting papers or new methods, then that would be interesting to go through as well and understand what are the variations compared to what we have learned so far.
Okay.
Okay, sounds good. Thanks everybody for joining. And if you're interested in Kaggle, we start in about 40 minutes.
Okay, take care. Bye-bye.
Yeah, thank you so much. It's been great. Talk to you in a little while.
Thank you.